In industry, cutting is a part of not just a matter of following shape. We also need to decide where to start, in what order to cut, and how to avoid unnecessary movements. What looks like a simple machine action is in fact a complex optimization problem. This question matters in many sectors, such as aeronautics, automotive, garments, and semiconductors. A better cutting path can save time, reduce costs, and improve production efficiency. Our research starts from a simple observation. In real manufacturing, cutting machines face many different situations. Some parts are nested inside others. Some cuts are shared by several parts. Some areas must remain attached for a while before the final cut. In thicker materials, even piercing the material has a cost. These cases are often studied separately. Our goal was to build one general framework that can handle all these situations in a consistent way. To do this, we translate the cutting problem into another optimization problem that is well known in operations research, the generalized traveling salesman problem with precedence constraints. In simple terms, we take a practical industrial problem and express it in a mathematical language that is more general and easier to solve with advanced algorithms. Our approach follows four main steps. First, we analyze the cutting situation and its constraints. Second, we transform it into a mathematical model. Third, we compute an optimal or close to optimal solution. And fourth, we translate that solution back into a cutting path that can be used in production. The results are promising. From a theoretical point of view, we show that this transformation is efficient and it preserves the cost of the original problem. In other words, solving the mathematical model gives us a cutting path of the same value for the industrial problem. We then tested the framework on real industrial instances. The computational results show that our methods can find optimal or very high quality solutions in a short period of time for many cases. That means that the framework is not only mathematically sound, but also practically relevant. The contribution of this work is twofold. On the theoretical perspective, it unifies several variants of the discrete cutting path problem within one modeling framework. On the managerial and industrial side, it opens the way to stronger decision support tools for production. More broadly, it shows how applied mathematics can support smarter production. Production can make better decisions, organize operations more efficiently, and use resources more effectively. Here, though, the example of cutting. This work is already a strong step forward, but also opens new directions. The next challenge is to improve performance with several cutting features appear at the same time, and to bring these methods closer to industrial CAD/CAM systems, with their further applications in Industry 4.0 or even resilient supply chain network designs. Our ambition is clear: to turn theoretical advances into practical tools for smarter manufacturing, thus improving our overall quality of life.